In this video, we're going to find the area between two curves. We're going to do a couple of examples. Here's our first example. The problem may be posed to you this way. Someone may ask you to find the area between the curve given by y equals 2x and the curve given by y equals e to the 3x for x between 0 and 1. So the first thing that I would do on a problem like this is sketch the curves. And if I'm graphing y equals 2x, I know that that's a linear function. And this is not going to be to scale. That's okay. We want to start at 0 and end up at 1. If x equals 0, y equals 0 on that line. And if x equals 1, y is going to equal 2. Actually, I'm going to put 2 way down here, because this is not to scale, but alright, so that's 1, 2. Now for y equals e to the 3x, this is an exponential function. It grows much faster. When x equals 0, we get e to the 0. Remember, any number to the 0 power is 1. So we're going to start there. And when x equals 1, we get e cubed. And that's about 2.7 cubed. Remember, e is an irrational number. I want to take e and raise it to the 3rd power. I get approximately 20, which is a big part of the reason why I could not draw this to scale. So when x equals 1, y equals 20 on that graph. So I just write not to scale. Okay, so e looks like this, that e to the 3x, and y equals 2x looks like that. And we're interested in the area between the two curves for x between 0 and 1. So we're trying to find the area of this region right here. Now notice, if I draw my rectangles vertically, the entire time for every rectangle that I draw, that exponential is going to be my top function. Even this rectangle down here, exponential is my top function, the linear function is my bottom function. The same would be true over here with this rectangle. The top is the exponential and the bottom is the linear function. Since that's true for every x value on this interval, for every little rectangle that I draw, it's pretty easy to see the top function is e to the 3x, and the bottom function is y equals 2x, and so we can just set up the integral representing the area between the two curves. So according to our formula, we've got the integral from a to b of the top function minus the bottom function. We're integrating with respect to x. X starts at 0 and ends at 1. And the top function was e to the 3x, so we just substitute that in. Remember what this is. This is your top minus bottom. And the bottom function was 2x. And you're integrating with respect to x, so don't forget your dx. Okay, now it's easy enough. You just use the fundamental theorem of calculus. Now remember, if you have e to a constant times x, the antiderivative is e to that constant times x, and we're going to divide by 3. If I was taking the derivative, I would do e to that power times the derivative of the inside, which would be a 3. So differentiating requires me to multiply by 3. When I anti-differentiate e to the kx, I have to divide by the 3. Over here, I'm going to bring my constant down, add 1 to the exponent, and divide by the new exponent. The 2's reduce, and we have the integral from 0 to 1 of this function. And when I substitute in 1, I get this. And when I substitute in 0, I get this. 1/3 times e to the 0, that's 1. Or 1/3 times 1, which is 1/3. And then minus 0 squared, which is clearly 0. So I've got 1/3 e cubed, and negative 1 minus 1/3 is negative 4/3. You could get a common denominator if you want to, but you don't have to. So that's the area between those two curves. And that one wasn't too bad. They told us what a and b were. They gave us those values for x, and it just so happened that this one was always the top function and this one was always the bottom function. So we just needed to graph it to figure out which one was which, and then substitute into the formula. Pretty easy. Now in this next problem, it's a little bit more complicated because a and b are not given to us. They ask us to find the area between this function and this function. Now, whenever I see that x squared, if there's x squared and there's no x cubed, there are no higher powers of x, this is a parabola when I graph it. And then this is a line. That's y equals mx plus b, where m is -1. So this is a line. So I'm just finding the area between a parabola and a line. The first thing we're going to do for this is to graph the two functions. We always want to start with that. So let me give you a list of steps. We're going to start by graphing the functions. I'll do the easy one first. Y equals -x. Looks like this. It goes through the origin, and the slope is -1. So that means we go down 1 and over 1, right? We said rise over run or fall over run. Fall 1, and then run to the right 1. So down 1, over 1, down 1, over 1, down 1, over 1, and just continue like that. And the pattern continues on both sides. Go back 1, up 1, back 1, up 1. I'm going to do it one more time. Back 1, up 1. And it's supposed to be a line. My graph's not perfect, but you get the idea. That's supposed to be y equals -x. Now for the parabola, this one's a little bit harder to draw. But I hope you remember from college algebra or pre-calculus 1 that y equals x squared is just a parabola with its vertex at the origin. So y equals x squared just looks like that. Now if I take that and I multiply by -1, that means you just flip it upside down. Do you remember what happens if we add 2 to that? I think you just take that whole thing. It used to have a vertex at the origin and be going down. Now we're going to move it up 2 units, and it's going to go down. So that's what our graph will look like. When x is 0, y is 2. Now if x is 1, y is going to be 2 minus 1 squared. 1 squared is 1, so 2 minus 1 is 1. And if x is -1, we're going to get the same thing. So it's going to look like that. Now when x is 2, 2 minus 2 squared, that's 2 minus 4. 2 minus 4 is -2. We're going to be right here. And the pattern continues, but we're not too concerned about that. I think I can see from my graph my points of intersection. X starts at -1 and stops at 2. So if I'm trying to find the area between these two curves, that area, I'm going to evaluate an integral from a equals -1 to b equals 2. Okay, so let's back up a little bit. What did we do? We graphed the functions. And then generally we want to find the points of intersection so that we can find a and b. I'm going to do that algebraically just to prove to you that those are the right answers, x equals -1 and x equals 2. And you might say, Miss Townsend, I don't need you to prove it, I can see it. And that's cool, but sometimes when you're doing this, it's not so obvious. And sometimes our sketches are a little bit rougher, and it's a little bit harder to see exactly where they cross. The fact that I went through all of these little points made a big difference in showing us that those are the points of intersection. Okay, so let's say you just had a rough sketch and you weren't sure where they met. You can say, how do you find the points of intersection? I hope you remember from pre-calculus, if I want to know where this graph crosses this graph, basically I just need the y's on this graph to equal the y's on this graph. This is the function y equals 2 minus x squared. And I want to know, when are the y values on that parabola equal to the y values here? It looks like, when is this y value equal to 1, while this y value is also equal to 1? Let's say we didn't know what the y's were. When is this y value equal to this y value? Well, to find that, I'm just going to set the y's equal to each other. So I'm going to call them y1 and y2 just to have names for them. Y1 is going to be the top function. Y2 is the bottom function, and this is pretty arbitrary. You could choose whichever one you want. You're setting the y's equal to each other, and now you want to solve for x. I've got a quadratic equation. The easiest way to solve a quadratic equation is to set one side equal to 0 and then factor if possible. I'd like to have a positive x squared term, so I'm going to add x squared to both sides and subtract 2 from both sides. So those guys are gone, and now I have 0 equals x squared minus x minus 2. Let's see if this factors. First times first is x squared, so I've got an x and an x. Now I need two numbers that multiply to give me negative 2 that add to negative 1. So product of negative 2 and a sum of negative 1. And remember, in order to get a product that's negative, one of these has to be negative and the other one has to be positive. So what I'm really looking for is two numbers that have a product of positive 2 that have a difference of 1. Well, 1 and 2 will work if one of them's negative and the other one's positive. In order for the sum to be negative, the 2 has to be negative. Negative 2 plus 1 is negative 2, and negative 2 times 1 is negative 2. So this is a negative 2, and that's a plus 1. And if this times this equals 0, that means either the first factor is 0 or the second factor is 0. If I solve this one for x, I get x equals 2. I solve this one for x, I get x equals negative 1. You say, okay, what does that tell me? That tells me that the y values are equal on the graph when x equals 2 and when x equals negative 1, which is exactly what we saw when we evaluated, or when we found that graphically. So we've graphed the functions. If it's not obvious from the graph, you want to find the points of intersection, and then you want to look at your picture and just say, is this an integral? If I'm finding the area between the two curves, should this integral be set up in terms of x or in terms of y? Or rather, if I draw my rectangles and I draw them vertically, will I always have the same top function and the same bottom function? If I do, that's probably the way to go. And then what if I draw my rectangles horizontally? If I draw my rectangles this way, will I always have the same right function and the same left function? If so, that's probably the way to go. And sometimes both ways work, and either one is fine. But in this case, notice what would happen if we drew our rectangles horizontally. From here, from this y value, which is negative 2, all the way to y equals positive 1. This line would be the bottom function, and that part of the parabola would be the top function. Or, it's not really top and bottom anymore. It's left versus right. These are the larger x values are on the right. The smaller x values are on the left. So we're going to do right and left. Right minus left to find that length. But I've got the line on this side and the parabola on this side until I get here, and then over here, I have the parabola on this side and the parabola on that side. Now that's not a problem. We can still work with that if we wanted to, or we could still find that distance between this side and this side, but that's two integrals. I don't have the same right function and left function all the time. The right function and left function, they switch. At y equals 1, the bottom function, which used to be the line, goes from being the line to being the part of that parabola. So we don't want to do that. We want to do this instead. Look what happens if I draw my rectangles vertically. That top function is the parabola all the time. Even if I draw a rectangle over here, top function is still the parabola. bottom function's the line, top function's the parabola, bottom function's the line. All the way across, all the possible rectangles I could draw, top function's the parabola, bottom function's the line. So I know I want to set everything up this way, and if I'm setting everything up that way, the width of that rectangle is delta x, so we're going to be integrating with respect to x. So area is the integral from a to b of the top function minus the bottom function, or you will see me sometimes write it this way: the top y value as a function of x minus the bottom y value as a function of x. And then we just need to substitute in our a and our b, substitute in our top function and bottom function, and evaluate the integral. Okay, so the a and b are bounds for x, so they tell us where x starts and where x stops. We're looking left to right. X starts at -1, and then we go through the region, and we stop at 2, and then the region doesn't exist after that. So our bounds are -1 to 2. Top function was the parabola. That was given by the equation 2 minus x squared. Bottom function was the line, and we're subtracting a negative x. The equation of that line was negative x. So we'll simplify a bit. Distribute the negative x is positive x. And then we just antidifferentiate and use the fundamental theorem of calculus to get our final answer. The antiderivative of a constant is a constant times our variable. Bring the -1 down. Here, power rule, you add 1 to the exponent and divide by the new exponent. When you bring the +1 down, here there's an implied 1. We want to add 1 to the exponent and divide by the new exponent. Plug in -1, plug in 2, and subtract. So we get 2 times 2 minus 1/3 of 2 cubed plus 1/2 times 2 squared. That's f of 2. And then we're subtracting 2 times -1 minus 1/3 times -1 cubed plus 1/2 times -1 squared. That's our answer, it's just not simplified. From here you can do the arithmetic and you're going to get your final answer. I'll do it pretty quickly. We've got 4 minus 8/3, that's half of 4, which is 2. I'm subtracting -2. That's going to be a -1 times -1/3 is positive 1/3. And that's a -1 squared, it's 1 plus 1/2. Or times positive 1/2 is 1/2. You could simplify in parentheses first and then distribute. I don't think I will. 4 and 2 is 6. Now I'll distribute the negative. So -2 is positive 2. We're subtracting 1/3 and we're subtracting a 1/2. So this is 6 and 2 is 8. -8/3 minus 1/3 is -9/3. -9/3 is -3. I took care of that and that and that and that, and I need to subtract a 1/2. So it looks like I have 5 minus a 1/2. So I get 4.5, which is 9/4. No, 9/2, excuse me. Yeah, that's 4.5. Or, I'm sure about that, that's 4.5. So that's the area between those two curves. Now we'll look at examples where you've got left functions and right functions, so that we're integrating in terms of y in another video. And we'll also look at problems where you have to do two integrals, where you don't have a choice. And we'll see how that plays out. Okay, I don't think I wrote through the entire outline of the method, so let's go through the outline of the method again. First we graph the functions, then we find the points of intersection. And then I was setting this up, and I needed to identify the top function and bottom function. Well, I guess we had to first decide, are we going to integrate with respect to x or with respect to y? And when you're making this decision, you're deciding based on whether or not those rectangles have the same top function and bottom function the whole time, or have that left function and right function the whole time. since these rectangles all had the same top function and bottom function, we wanted to integrate with our rectangles being vertical. So I guess I'm really deciding between vertical and horizontal rectangles. Since I had the same top function for all the vertical rectangles and the same bottom function for all the vertical rectangles, I went with the vertical rectangles. And whenever you've got vertical rectangles, their width is delta x, so you're integrating with respect to x. So we decided on that, and then once we made that decision, we identified the top function and bottom function. You substitute those into your integral, and of course you substitute the appropriate bounds. And those bounds, A and B, came from the points of intersection that we found earlier. And then the last step was to evaluate the integral using the fundamental theorem of calculus. Easy breezy.